Okay, so we're going to start with acid-base indicators. And in general, an indicator is a substance that changes color. When does it change color? It changes color in the presence of other chemicals. So if you remember in our solubility unit, we had Ag plus, which would react with Cl minus, and we would be titrating the Cl with the Ag, and we'd get AgCl. And then once all the Cl was gone, Ag plus would react with chromate, which gives us Ag2CrO4, which is red. So you would see that red color as soon as all the chloride was gone. So our indicator in a solubility titration this guy is our indicator. Because it changes color. Once all the chloride is gone, it reacts with the silver. And if you've forgotten, that little guy there means with. Yes?
So if I have a solution with AgCl as the precipitate, and then I put AgCrO4.
No, not AgCrO4. You would put NaCrO4.
You put in CrO4 with like
Na, yeah.
That would mean that it would react with the Ag.
Any Ag that's left over.
Oh, it's left over. So
yeah.
But if I'm at saturation, then it won't react.
No. So basically what would be happening is down in your flask, you would have Cl. Yes, you would add Ag, it would react with the Cl, add the Ag, reacts with the Cl, because Ag likes being with chloride better than chromate. Okay? And so you keep adding it until all the chloride is gone. At that moment, the next drop of silver that you add will get together with the chromate. And once it gets together with the chromate, then you see that red color. And you'll be like, oh, my reaction is done. All the chloride is gone.
Okay.
Yeah? Yeah. Now, in this unit, we will be focusing on acid-base indicators. And acid-base indicators are something very particular. An acid-base indicator will change color in the presence of an acid or the presence of a base. And it does that because it is made of a weak conjugate acid-base pair. And it is a pair. So an acid-base indicator is two species together. Not just one. What you've got is you've got a molecule that has a proton on it, and we're going to call it HIN, IN standing for indicator. Okay, so we don't have a formula for it, but we're going to call it HIN. There we go. Yeah, we got HIN, and we have the unprotonated form, IN minus. So that is just a conjugate acid-base pair. HIN minus and IN minus together are the indicator, are the acid base indicator. And each one will change at a specific pH range. Okay, acid-base indicators, they change color at a specific pH or pH range. So everyone is different. And if you want to take a look at what color, what range they change color at, you can grab your pink data booklet and turn to page 7. If you don't have a data booklet, you're going to want to go get one. So there are some here. Watch the pink one, there's the pink ones up there. Page 7. So, for example, methyl violet changes color from pH 0 to 1.6. Thymol blue changes from pH 1.2 to 2.8. Phenolphthalein, do you remember phenolphthalein? Phenolphthalein changes between 8.2 to 10.0, which is not at neutral, but we'll find out why we can use it even though it's not changing at pH 7. Okay, when we go from acid to base. But we'll get into all of that later, okay? And on this chart, it also tells you that it goes from colorless to pink. The colorless is what is happening below 8.2. The pink is what is happening above pH 10. And in between, you get that, you remember that light pink color we were aiming for? That's what we call the transition point, okay? And that's the in-between color, all right? So this one is a light pink color. What is the color when you have, say we had a yellow and red. What does yellow and red make? Yellow and red make orange. So for alizarin yellow, for example, alizarin yellow would be orange between 10.1 and 12.0. It would be yellow below 10.1. It would be red above 12.0. Does that make sense? Okay, so orange in that range. If you go below it, it's going to be yellow. If you go above it, it's going to be red. What do we get if we combine blue and yellow? We get green. Why am I asking you such simple questions? Every year there's always one person whose kindergarten teacher didn't do their job for whatever reason. And they never learned that yellow and blue make green, okay? But for, say, indigo carmine, if we were in between 11.4 and 13, so say our pH was 12, the solution would be green. If we were at pH 14, it would be yellow. And if we were at pH 10, it would be blue. What's our last color combination? We've got blue and yellow. We got yellow and red. What else can we combine? Red and blue. What do those make? Purple. Okay? So you are responsible for knowing those color combinations. Hopefully for most of you, you're like, why are you teaching me this? I learned this in elementary school. But just in case, like I said, every year there's somebody who missed it somehow. Maybe it was during COVID. Who knows? Yes. Okay. So let's go back then here. What on earth is happening? Oh, that's the wrong one. That's acid-base 1. I don't want that. I want Acids 2. What is happening? Where did it go? So, hold on. Okay, let's try this one. Yeah, there we go. Okay. Yes.
So these indicators, are they chemical compound like methyl violin?
Yes. Yes. So let's take a look. Let's take a look. We actually have the structure of bromcresol green, for example. Okay. So you don't need to know what this structure is. All you need to know is that they're usually kind of big and bad. Okay. They involve a lot of double bonds and ring structures and things like that. It is the movement of those ring structures that usually allow electrons to go up and down and to emit different colors. Okay. And by changing whether you have a hydrogen or whether you have no hydrogen, it changes the color. Yeah? So if we have the hydrogen on there, the whole thing is yellow. You don't have to color it yellow because it says the word yellow here. All right? Over here on the right, without the hydrogen, that turns the whole thing into the color blue. What?
If it turns green, what does that mean? Like, where does hydrogen go?
Oh, what it means is that there's not just one molecule. There's like millions of molecules. So if you had 1 million molecules and half of them were yellow and half of them were blue, then you would see green. Yes? Okay. So some of the molecules are going to be yellow. Some of the molecules are going to be green. Because this is a weak acid and base, it sets up an equilibrium. And if it's an equilibrium, we can shift it to the left or shift it to the right, depending on what we add to the system. So now, do we want to be writing out this big complicated formula every time we use bromcresol green?
Yeah.
Probably. Okay, you might, I don't. So I'm just going to call it HBG for bromcresol green. There's something or other BG, and it's got an H on it. And then we have the other form, which has no H on it, the BG minus. And this is a weak acid-base equilibrium. Like this is a weak acid. This is a weak base. Yeah. You cannot have an indicator that's made with a strong one because you need to have that equilibrium for it to be able to shift between the two colors. So it allows it to shift between the two colors. So if we know the particular indicator, we might give it BG for bromcresol green. We might use MV for methyl violet. If we just know it's an indicator, we can just use IN or IND for indicator. Yeah? So remember, bromcresol green is a mixture of both. Those. Bromcresol green is not just one of them. It's not just HBG. And remember, in any equilibrium system, even if we push it like all the way to the right, there's still going to be like a little itty bitty teeny weeny amount, like, you know, going the other way. Yes? Even if we push it all the way to the left, there's going to be a little bit itty bitty teeny weeny amount. Okay. All right. So here we have bromcresol green. We call the form that has the hydrogen the acid form of the indicator. And we call the one that has no hydrogen the base form of the indicator. So if we have an acidic solution, that means our hydrogen concentration is high. What will that do to this equilibrium? It will shift it to the left. So the equilibrium is shifted left. That means that HBG concentration will be high and Bg minus will be low. So we are going to see what color? We're going to see yellow. So we can say that HBG is the predominant species. Remember, predominant means main. Those mean the same thing. And the overall color will be yellow. Why will bromcresol green be blue in basic solution? In basic solution, we have lots of OH minus. What does OH do with H? They react. We get OH minus plus H plus, and those react to form H2O. What does that do to the concentration of hydrogen? This gets used up. Therefore, concentration of hydrogen decreases. And if our concentration of hydrogen decreases, which way does the equilibrium shift? To the right. And if it shifts to the right, that makes the concentration of HBG low, and the concentration of Bg minus high. And that means, what color are we going to see? We're going to see blue. So therefore, Bg minus is the, what's the word that means main? Predominant. Yeah, of course.
For this one, like the pH range is about like 7, so we can say yes, so we can basic.
Yeah.
But for the ones that there's something
Then we're going to say more acidic than the transition point and less acidic, that more basic than the transition point, which is where they change color. So overall, this the color of the solution will be blue. Indicators transition. In other words, they change between colors. When the acid form, HBG, and the base form have similar concentrations. So they transition when the concentration of HBG is approximately equal to the concentration of Bg minus. In other words, when the concentration of yellow is approximately equal to the concentration of blue. because when you have the same number of molecules of each, you will end up with green. Which just answered the next question. What color will bromcresol green be when it is transitioning between the two? Green. Yes, purple, absolutely. Okay. Okie dokie. I know I don't have to do this, but like, oh, no. Yeah. That should be yellow. That should be blue. It'll just make me happy if I've got those colors on there. There we go. All right. Next page. When the acid form is exactly equal to the base form. So when we have the concentration of H, for example, HBG is exactly equal to Bg minus, we call that the transition point. Okay, so our transition point is when HIND is equal to, I need to fix that. I'm not consistent between my two things. You can pick whether it's IN or IND, but you should not like switch halfway through. So this should say concentration of HIND is equal to the concentration of IND minus, or it should say concentration of HIN is equal to the concentration of IN minus, but I need to fix that because I've mixed and matched, and that doesn't make any sense, right? Fix. Now this makes something special happen at the transition point. So if we were to write our acid-base equilibrium that has our acid form and our base form, acid form and our base form, and at the transition point, these two guys are at the transition point, the TP, transition point, they're equal. And if they are equal, what can we do with them? We can cancel them. And if we cancel them, what are we left with? Ka is equal to H plus, not any old H plus, but H plus at the transition point. And because that is a lot of words to write, you can say Ka is equal to concentration of H plus, and then you can just write Tp down at the bottom. That means. So if you know the hydrogen ion concentration, you know the Ka. So if you had a solution and you had the indicator was at its transition color, and you used a pH meter to find out the hydrogen ion concentration, you could figure out what the Ka of that indicator is, because it would be the same as the hydrogen ion concentration. So Ka of the indicator equals H plus at the transition point. That also means that if we were to take the negative log of everything, what do we get if we take the negative log of Ka? We get pKa. So pKa of the indicator, what do we get if we take negative log of hydrogen? pH. So pKa of the indicator is equal to pH at the transition point. So all three of those things are true at the transition point. HIND equals IND minus, Ka equals H plus at the transition point, and pKa equals pH at the transition point. Those three things are true. This allows us to do a couple of things. If I give you the Ka of an indicator, you can find the pH. You can say, oh, I know my Ka. If I know my Ka, I know the hydrogen at the transition point because those two are equal, and then you just change it into pH by taking the negative log. If you know the pH at the transition point, then you can go backwards and you can say, ah, I know the pH. I can convert that into H plus, right? How do you do that? Yeah, 10 to the negative pH. Okay, and you find your hydrogen ion concentration, and then you know the Ka of the indicator. So on page 7, we've already looked at page 7. We have the indicator, the pH range, and the color change. So we're going to use that data to do some math. What is the pH at the transition point for methyl violet? And I've put the data in here so we can take a look at it. So methyl violet changes color from 0 to 1.6. So what color is it below pH 0?
No.
It's yellow. Above pH 1.6 it is blue, and in between those two it is green. Do not worry about, well, what if it's exactly at 0? What do I do then? Is it yellow or is it green? I'm not going to give you exactly pH 0. Okay, I'm going to give you pH negative 0.1, or I'm going to give you pH 0.1. All right? And don't worry about the shade of green in the middle. Don't be like, oh, it's 0.1. That's a yellowy green. No, it's just green. Just be simple. Okay? So you need to know that this whole thing, if we're at pH 0, below 0, it is yellow. Above 1.6, it is blue, and in between those two, it is green. So what we've got is we have HMV is yellow, and we have MV minus. Why do I feel like HMV is like a store? Is that a store? H&M is a store, but I feel like HMV might have been like a audio video store when I was younger. No, it was like an audio video store, not a clothes store. But I could also be completely wrong because it was a long time ago. Well, we're not going to look it up right now, but maybe when we're all done, because we might finish early today. Okay?
Jumping up and down.
Okay. So when we're in between, we have a mixture of the two. Yes, it will be more bluey green towards the top. Yes, it will be more yellowy green towards the bottom, but we're just going to call it green. I will just come over and smack you around.
Oh.
Or maybe I'll just pretend to smack you around, because that will probably be better for keeping my job. Okay? I'll just come over and be like, Ben, what are you doing? Don't do that. I feel like I'm conducting now.
You're gonna be like, you're gonna be the blue book.
Ooh, what's the blue book?
No, the blue book is like this thing. It's like, do you know the blue book is for? It's for the teachers. Like, no.
I'm sorry. Damn, I'm sorry. Damn, sorry.
In order to make sure, in order, I guess, to keep the whole, to show that they're holding accountability with teachers. Any teacher who's done something weird or wrong, they get put into the blue book.
Oh.
And as some cases get released like every.
Oh,
every couple of
okay.
years.
I did not know it was called a blue book.
It's called a blue page or something like that.
I don't know.
I went and I looked, and some of these teachers, they're wilding out here. Like, some of the stuff they're doing is crazy.
That's why I never worry about what I do, because there are so many people who do not lose their jobs and they do crazy things. So, hang on.
Domino's for really sure.
Yeah, you guys absolutely have to be here until the bell rings. That is what is required by law. Yes, Chelsea? Yes.
Oh, this is scary.
Okay.
This is fine.
Yes,
Can you go to the water?
you can go later.
Sure.
Okay.
That sounds so weird now. I feel like we're recording this soon. Go later, go later.
Well, we're right in the middle of a lesson right now. You can go when the lesson is done. Okay? Now, remember we've got this equilibrium, right? We've got our HMV. Where is it? Okay, so we got our HMV, and we've got our H plus, and we've got our MV minus. And so if we have a higher pH than the transition point, that means that we have a lower hydrogen, which shifts it to the right, which means that MV minus is the predominant species. Does that make sense? Okay. And if we have a lower pH compared to the transition point, that means that you have a higher hydrogen ion concentration, and our equilibrium
For me, a secret and very happy when the solution is really acidic,
yes,
it's yellow.
yes,
But when it's more basic, it's blue.
yeah. When it's more basic than pH 1.6, it's blue.
Okay.
Okay.
When it's at neutral, it's green.
No, not for this one. When it's in between pH 0 and 1.6, it is green. For this indicator, because its color change range is pH 0 to 1.6.
Right.
Okay?
But that doesn't mean a solution is neutral.
That does not mean the solution is neutral. No. So some things change at neutral pH, some things change at an acidic pH, some things change at a basic pH. Yeah. Each one changes at a different pH. So now we have our pH at the actual transition point, and that is where HMV concentration is equal to MV minus, and it is halfway between 0 and 1.6. What is that pH? 0.8. It's at the halfway point. How do we find a halfway point? We take the average. In this case, it's really easy. You just take 1.6 and divide by 2. But normally, you would show your work by saying, I am calculating pH at the transition point. Make sure you write this. Write this. Okay, show what you're calculating. And then you'll put your two numbers, and then you'll divide by 2, and then you'll get whatever you get. Now, that gives you that, and we can try finding the Ka of methyl violet. And actually, before it's written down there, but let's just try it up here. If I know the pH at the transition point, what else do I know? I know the concentration of the hydrogen ion, concentration of H plus at the transition point is equal to 10 to the negative pH at the transition point. You don't have to write that every single time, the TP up there, but I'm just writing it for. And so that's going to be 10 to the negative 0.8. And 10 to the negative 0.8 is if we know hydrogen at the transition point, what else do we know?
You know the concentration is always minus.
Well, we do know that, but what are we trying to find? What is special about hydrogen at the transition point? Hydrogen at the transition point is equal to Ka of the indicator. Okay? And so that is equal to Ka is equal to 0.15. How am I doing with my sig figs? Oh.
Not thinking of properly.
So, how many sig figs in my pH?
One.
1 sig fig. So, how many should I have in my Ka? 1. So, that's going to become 0.2. Is good? Okay. And the stuff written at the bottom of the page is just what we did up here. So, okay, now you get to try with phenol red. So you've got the data for phenol red, or you can look in your pink book, doesn't matter, it's right here. You're going to tell me the color of the acid form of phenol red, the color of the base form of phenol red. The color at the transition point, and then you're going to find the Ka. If you finish example 7, you can try example 8, which is going backwards.
That was a CD. That was a CD and like
Yeah, HMB. I knew it. I knew it. Okay, I didn't really know. I had a few, but I wasn't.
it was. I just said
Yes. HMV was an audio-visual store, an AV store.
7.3 years.
You have to do that.
Yeah, sure.
Like 0.00000005.
So like, can I get a second?
1, 2, 3, 4, 5, 6, 7, 8. 5.8. 5.0.
One, six.
Yes.
Big. Are you taking it? We can't talk to you about it.
Who the hell is Spawn John Steven guy, bro?
What are you talking about?
I've never heard
Steven.
No, everyone I know is like music. Everyone is. I've never heard that. I've never heard that. No, Abraham always no. That's not.
Abraham. No, but then I was looking at the account and they kept posting. I'm like, who is he? Oh, it's the guy who did the phone guy.
I can't remember what we were talking about.
Oh, you're not gonna look at that. Okay, that's your deal.
Oh, wait, I'm
That's why I love this little beast. It's so good. It does everything.
Put it in thickness, I don't ask him that, oh, pay to win, I got it.
Yellow shoe.
Honest, he's not honest.
That was trying to sell it. It's funny. I would have back in that page.
So if we had a low pH, okay, which is like below pH less than 6.6. So if our pH is less than 6.6, that means our hydrogen ion concentration is high, which shifts this to the left. And when we are less than 6.6, remember we are yellow. So that means that this is yellow. If we have our pH is greater than 8.0, that means that we have less hydrogen. And that means it's going to shift to the right, which means that we're going to have PR minus, which is going to be red. So basically, when you look at this, you can say this is always the acid form. This is always the base form. The acid form is always on the left. The base form is always on the right. This is always going to be like HIND. This is always going to be IND minus. Acid form on the left, base form on the right. What color will phenol red be at its transition point? Orange. Which rhymes with door hinge. Isn't that awesome? Door hinge. Door hinge. Door hinge. Orange. Anyway, how do we go about finding the Ka? We need to find the, and before that we need to find the pH at the transition point. So make sure you write that and show that you have taken the average. 6.6 plus 8.0 divide by 2 is that 7.3?
Yeah.
Okay, excellent. And now our Ka is equal to the hydrogen ion concentration at the transition point. And hydrogen is equal to 10 to the negative pH, which is going to be 10 to the negative 7.3, which is 5.0119 times 10 to the negative 8, which looks like a lovely number with not the correct sig figs. How many sig figs should we have in our answer? Remember, in pH, in any p-value only digits after the decimal are significant. And so that means we have 1 sig fig, which means that we need to round this to 1 sig fig, 5 times 10 to the negative 8. Does Ka need a unit? It does, but I've put this at the beginning. If I had just done hydrogen, I would need a unit. But because I've put this here, I don't need a unit. So if this were gone, then I would have to say molar, and then I would have to say Ka equals H plus, and then write it without a unit. Does that make sense? Okay, but if I put Ka here at the start, then I'm like, don't want a unit at the end. So no unit. Don't have to write it twice. Does that make sense? Yeah, okay, cool. Have you guys tried the next one? Okay, if you have not tried it, let's go. Let's try it. It's going backwards this time. And I don't know, apparently nobody in the first block could figure out that this was all example 8. So A, B, C, and those are all the same questions. So they all relate to the same data. Okay? So they're all part of the same question. Thank you very much. Awesome. Thank you. So at what page? So you know the Ka. Oh, yes. What it, yeah, you got those times yes. No worries. if I know that Ka is 3.2 times 10 to the negative 5, what else do I know?
You know the concentration of hydrogen.
I know the concentration of hydrogen at the transition point is 3.2 times 10 to the negative 5. And if I know that, can I find the pH?
Yeah.
Yes. Ah. So if it's 4.4949, how many digits should I have here? I've got 2 sig figs here because that's not a p-value, so everything is significant. And now this is a p-value, so only after the decimal, so that means that I'm going to have 2 sig figs here, so this is going to round to 4.49. And then if we want to know what color the indicator is in a solution of hydrochloric acid, what we can do is we can say, well, what is the pH of the hydrochloric acid solution? Well, because HCl is a strong acid, H plus is equal to HCl, which is equal to 1 times 10 to the negative 6. And then if we find the pH, that's the negative log of 1 times 10 to the negative 6, which is 6. So our solution is pH 6. What color will our indicator be in that solution? What is the pH at the transition point? 4.49. That means that below pH 4.49, we have the acid form, which is red. And above 4.49, we have the base form of the indicator, which is blue. And if we have a pH of 6, well, 6 is over here somewhere, right? pH 6 is greater than 4.49. And so we're going to have the base form of the indicator. Even though we've put it in some acid, it's not enough acid, right? Because that's quite a dilute acid there. Yeah, 10 to the negative 6 molar. That's really dilute. So it will be at pH 6, the indicator will be blue. And that means that what is the predominant form of the indicator? What's the predominant form of the indicator?
No, but how is it if it's at 6?
6 is higher than 4.49. 4.49 is where it changes color. It's not changing at pH 7. That's what you have to get your head through, is that very few indicators actually change at pH 7. This one changes to its base form way down at 4.49. Okay? All right, one last note before we are done. As we go down the acid-base indicator chart, what happens to the pH at the transition point? So as we go this way, what's happening to the pH at the transition point? It is increasing. And if it is increasing, what is happening to the pKa? It is also increasing because these two are the same. Yes? And if pKa is going up, then Ka is going down. Because remember, p values and their regular values go opposite directions. If you have a higher hydrogen ion concentration, the pH gets lower. If you have a low pH, the hydrogen ion concentration gets higher. Therefore, is methyl violet the strongest or weakest weak acid of all the indicators?
Weekend.
It is the, let's find out. What is our pKa for methyl violet? 0.8. And that means our Ka is 0.2. Oh, I guess we should actually say that. As Ka decreases, what happens to the strength of the acid?
Wait, no, actually, increase. How is it decrease? If the case is decreasing, that means that there's more reactants than products, which means that H plus is more, which means that acidic form is more than basic form.
So if Ka is smaller, that means we have less H plus and A minus. And if we have less of the ionized, the acid is less ionized. So if Ka is smaller, less of it is ionized, the acid is stronger or weaker? Okay, so a smaller Ka means the acid is weaker. A larger Ka,
Oh my god, we established this like this. Oh my god. I forgot. In the freaking acid. Oh my god. Okay.
so why did I put a big gap in between acid 1 and acid 2? So that you could forget and then remember. Relearning curve. Yeah. Was it? Oh my god. That's fantastic. I love that. Yes. Oh, stronger. That means I stopped paying attention to what I was writing and my brain just wrote something. The acid is larger. Whoa, I'm a big fat acid. I'm the sumo wrestler of acids. Okay. So our pKa is 0.8 and our Ka is 0.2. Now down at the bottom, what is our pKa of indigo carmine? It is not 13.2. It is 12.2. There we go. And so our Ka is 10 to the negative 12.2, which is 6.3 times 10 to the negative 13. Well, it's actually just 6 times 10 to the negative 13 because we only have one sig fig. And so you can see here we have our very small Ka. This is our smallest Ka. And up here we have our largest Ka. Which of the indicators is the strongest acid? Sorry, yes. Huh? Huh? Therefore, methyl violet is that's what we're getting to. Yeah. Yeah. If we have the largest Ka, if we have the largest Ka, methyl violet, it must be, is it the strongest or weakest acid? Strongest, because strongest have the largest Ka, strongest acid.
Also, like, it's the pH that would indicate that.
So that means that HMV is the strongest acid indicator. That means that HIC, by the way, I always say this when I introduce indigo carmine. If anyone wants to have a really awesome, ultra geeky name for their child, first name, middle name, indigo carmine. Nice. Yes. You'll notice my child is not named Indigo, but you know,
Boy, isn't he?
he's a boy. You can name a boy Indigo.
It's so stupid.
Wait.
in a way. That's weird.
Like it's a color.
I want to name my child yellow.
I thought you were.
You know what's so weird?
Yeah.
People would name their kid Blue, right? Like I could see someone naming their kid Blue, but I could never see anyone naming their kid Yellow.
Like pink.
Red? Yes, you could name somebody Red, especially if they had red hair.
Oh yeah, you could actually. Red is actually maybe not be a name.
It's actually a fairly common as a nickname, if not as a, yeah. But Yellow? Never heard anyone named Yellow. Your homework.
Oh, my God. Wait, but Spence, are you going to take a lesson tomorrow?
6, 7, 8, 9. Yes, I'm teaching tomorrow.
No.
So
You
like,
need to call skipping.
Yeah.
I'm skipping, bro.
Yeah, I'm done in a row.
So if you are planning on skipping tomorrow,
Wait.
hang on, you're not allowed to skip tomorrow.
Yeah.
So don't skip tomorrow, obviously.